Okay, I'm Pranav from Polytechnico, and I'm going to discuss about a new instrument that we're building, almost built at Polytechnico. So this is portable time domain diffuse optical broadband spectrometer for assessment mainly on heterogeneous media. That's most biological issue. Anyway, let's quickly get into the layout of the setup that I'm talking about. So we have this supercontinuum fiber laser that has signal from 450 to 750 nanometers. It's from NKT, and which this is on the signal side. So the supercontinuum is then is sent to a prism, and the prism is used as a wavelength selector. So you rotate the prism and focus the light into the source fiber using a lens. So by rotating this prism, then you can choose your wavelength, and this source fiber is then sent through a neutral density filter, and it is given as the input to a fiber optic switch, which allows the change of the position, which corresponds to the different source detector separations as shown here. Then on the detection side, we have 1 millimeter SMA fibers connected to two detectors, both more or less in-house built, with a very good responsivity over a wide range from 600 to 1300 nanometers. So from 600 to about roughly 1000 nanometers, we have the silicon photomultiplier, and from 1000 to 1300 nanometers, we have the PMT, in-gas PMT, and both of them are then connected to the PCS-PC boards, which are then connected to an industrial PC for the analysis and the acquisition. So a very interesting point with this system is it's completely automated. So be it the neutral density filters or the rotation of the prism, the switch. So it's a very well automated system. And a few words on the data analysis. So this multiple source detector separation data is then fit to a two-layer model, which can in a sense retrieve your optical properties of a two-layered model, like the top and the bottom layer, and also the thickness of the top layer. With that, I'll come to some of the key features of this system and then a few initial results. So firstly, some interesting features. Firstly, the use of a fiber optic switch. Though this switch leads to a little reduction in the input power, it's a very important equipment in this particular system, because firstly it improves the acquisition, reduces the acquisition time due to automation, and more importantly it avoids the repositioning error, which is a very huge problem, especially in clinical scenarios. Secondly, the use of a reference arm. So I'm sorry, I forgot to discuss the reference arm when I was explaining the system. So this is a very standard procedure, at least at PolyMe. So where we take out part of the input signal and directly couple it with the detectors at a particular time distance away from the actual measurement. So this can be used as a reference, and it is very useful to compensate for any inaccuracies due to any kind of a thermal drift or of the laser or some temporal distortion due to any reasons. And some other interesting features: the use of graded index fibers on the source side to avoid pulse broadening. Then the robust and compact detectors, which are again very useful in the clinical scenario. So just to give you an idea of how fast the system is, to have a typical acquisition of a 51 wavelength broadband measurement, it takes about 1.5 minutes. So with that, let's go to some initial validation that I performed using the system on phantoms. Firstly, here you see validation on silicon-based, epoxy-based phantom. So this is the measurement. Maybe it's not very clear from there, but this is the measurement at 3 different source detector separations and 1 in transmittance geometry, the dark blue, and absorption and scattering. And you see that for a homogeneous phantom, you see the more or less exactly the same optical properties. Then we went on to perform some validation on heterogeneous media. So this is biological media comprising of ex vivo animal tissue. For the top layer we considered veal, and the bottom layer we considered lard tissue. And so these here are the reference homogeneous spectra. So these are measurements made on bulk samples of these two materials and analyzed using a semi-infinite model fit. And here these are the insert the spectra using the combined meat sample as a two-layer media and measuring on it again and using analyzing it using semi-infinite model of fit. And instead on the bottom you see here the two spectra are a comparison with these reference values and the retrieved optical absorption properties of the top and the bottom layer. Here you see there is a very good agreement in both the bottom and the top layer, very well retrieved. Typically the agreement is under, the coefficient of variability is under 10% throughout the spectral region. With that, some initial in vivo measurement, acquisition and analysis as well for the two-layer model. So here you see we may perform a similar measurement on a healthy volunteer's head, and these were the retrieved absorption spectra. So the top layer here, the top layer was assumed to be roughly 12 millimeter. In this case, we in fact fixed the top layer in the analysis model, as this would help improve the analysis. And so we fixed it to 12 millimeter, wherein we are more or less sure that the top layer consists removes any kind of a contamination from superficial skin or skull, and the underlying layer we see is predominantly brain. And so when we use this particular absorption spectra and try to perform tissue constituent concentration retrieval using a linear fit of all the tissue constituent spectra, so these are the results that we got. One really interesting result here is that regarding the retrieval of the collagen content, in the top layer you see some significant amount of collagen, but in the bottom layer, which we expect to be the brain, we see literally no collagen content. And we know that collagen is the important constituent which makes up the skull. So here we can be quite sure that in the retrieved underlying layers absorption, you see literally no collagen content, which means that there is no contamination from the skull in this particular absorption spectra.